Hello, teacher Gan. Today we will go to presentation project through heat transfer. The first is its introduction. This project focuses on the detailed design and simulation of an air heater, heat exchanger, specifically engineered to produce hot air at a temperature at 1800 Celsius for use in the aforementioned coal and biomass combustion project. The design specifications stipulate the use of an electric heater providing 1,250 watts of power with a maximum tube surface temperature of 1000 Celsius. The heating elements are arranged in a staggered tube bank configuration to maximum heat transfer efficiency between the tube surface and screw. And the main objective of this project is to perform a comprehensive thermal and fluid dynamic design of the structure tube bank air heater to achieve an outlet air temperature of 800 Celsius under the specified volumetric flow rate of 1.42 cubic meter per minute, which corresponds to an approved velocity of 2 meters per second across the air inlet. Furthermore, the design will be validated by conducting an engineering simulation using SolidWorks simulation to model the fluid flow and heat transfer characteristics, ensuring the performer meet all stipulated design requirements. The next is the assumption. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 assumptions. The first assumption is steady state operation. The second, negative heat radiation. And the third, designing a triangular pattern to bundle SD and ST. And the fourth, TI 25 Celsius. And fifth, SD 52.25 mm. The third, ST 52.25 mm. And 7, NT 6, 8, NL 14. And the last is NT 84.
Okay, for calculation, the average Nusselt number is calculated using the Su-Cocat correlation. This dimensionless number relates convective to conductive heat transfer, giving a value of 38.263. This is then used to find the average heat transfer coefficient and this equation. This result is 57.176. Next, find the outlet temperature is found via an energy balance for the tube bank. This yield is 796.9 Celsius. The long mean temperature difference is calculated to find the effective temperature driving force. It's calculated as 490.476 Celsius. And next, the heat transfer rate per unit length. Use the formula this. The result is 403.265 kilowatt per meter. The total heat transfer rate for bank length is this equation, resulting is 133.078. And the last one, we need to find the pressure drop. The The pressure drop across the two banks is calculated using a modified C Weisbach equation. The friction factor is 0.51 and correction factor S1 are obtained from a correlation figure. The final pressure drop is 64.120. Go to the next topic.
Welcome. In this presentation, we will walk through the calculations for analyzing heat transfer in a crossover over two blank or two bundle. So, we begin with our given parameters for this problem. The length of the tubes L is 330 millimeters, D or the diameter is 35 millimeters. The power P is 1250 watt, and the surface temperature of 1000 degrees Celsius. The outlet air temperature TO equals to 800 degrees Celsius, and the volumetric flow rate Q is 1.42 cubic meter per minute, and the U infinity or upstream velocity of 2 meter per second. So, first we need to determine the longitudinal pitch SL using the formula relating diagonal, longitudinal, and transverse pitch. We find that SL is the square root of SD squared minus ST divided by 2, all square. Okay, plugging in the values, we calculate SL to be 45.5 millimeters. Next, we will establish the temperature needed to find the properties of air. We convert the given inlet and outlet and the surface temperatures from Celsius to Kelvin. Here, T infinity I to be 303.15 Kelvin. So, to evaluate the air properties, we use the mean fluid temperature or bulk fluid temperature, which is the average of the inlet and outlet temperatures, calculated to be 688.15 Kelvin. Now, using this mean temperature of 688.15 Kelvin, we can find the thermophysical properties for air from standard tables. Okay, for air at 688.15 Kelvin, we got the density of 0.499 kilogram per cubic meters. The specific heat Cp is equal to 1075 joule per kilogram Kelvin. V or kinematic viscosity is 67.81 times 10 to the power of minus 6 square meter per second. K or thermal conductivity is 0.052 watt per meter Kelvin. And last one, the prime number PR is 0.695. And now we need the properties of air at the surface temperature of 1073.15 Kelvin, and we get the prime number of 0.719. Now, we have to determine the maximum velocity Vmax within the two blank right here, right? Which is essential for calculating the Reynolds number. For a stacker, alright, stacker arrangement, we first check the condition to SD minus D more than ST minus D. Is it true or not? Okay, our values, our plugging in all the values turn out to be 34.5 more than 17.25, which is true. Therefore, Vmax is at A1 right here, or ST minus D. This condition tells us that the maximum velocity occurs at the transverse plane. We use the formula Vmax equals ST divided by ST minus D times V, or the upstream velocity. So this gives us a maximum velocity of 6 meters per second. With the maximum velocity, we can now calculate the maximum Reynolds number using the equation low Vmax D divided by mu, or Vmax D divided by B, the kinematic viscosity. Plugging in all the values, we got Renault maximum Renault of 3096.98. Okay. Now, next we have to find the ratio of ST but divided by SL. Since this is less than 2, here, right? Less than 2, we can determine the constant for the Sue-Coccus equation. From the tables for stacker of configuration, we find the constant M is 0.6 and C1 is calculated to be 0.360. Finally, for stacker arrangement with 14 rows, the correction factor C2 is found to be 0.983. This value will be used in the final Nusselt number calculation. And the C2, the 0.983, we have to do the interpolation to get this value right here.
I will talk about the design of our air heater. So here we can see the dimensions of our air heater with a length of 641.5 millimeters and a height of 315 millimeters. And the thickness of it is 330 millimeters in order to fit in the two bundles inside. Here's a section view of our air heater with a bit of simulation, and we can see the temperature as well. So along the horizontal direction, we have 14 tubes, and along the vertical direction, we have 6 tubes. So as we can also see from the simulation that as the air flows passes each tube, the temperature gradually increases from the start at 20 to by the end it is at around 6 to 700 and at some point even 800. We can see that it is 800 at the center, but on the upper and the lower end it tends to be lower than 800. So this might be caused from some error. And here is another view of our result. We can see that the top and bottom is lower in temperature compared to the center. And as for the conclusion, uh, we have built a heater to heat the air from 30 Celsius to 800 Celsius, but we can see from our simulation that there is a bit of error where the temperature reaches 800 only near the center, but on the upper and lower it does not reach 800, which could mean that there are some marginal errors from either the simulation because when comparing it to our calculation using equations, simulation takes in account of real physics and some real effects, maybe turbulence, or it could be some other properties that could affect the temperature. That's all for it. Thanks for listening to our presentation.